Okay, what if I told you that the two biggest mysteries in the entire universe, dark matter and dark energy, aren't two separate problems at all? What if they're actually two sides of the very same coin? Well, a brand new framework is suggesting exactly that. And honestly, it might just change how we see everything.
Just to set the stage, think about this. Everything we can see, everything we can touch, all the stars, the planets, entire galaxies, you, me, all of it makes up less than 5% of the universe. The other 95%? It's a total mystery, split between two invisible heavyweights that completely run the cosmic show. So on one side, you've got dark matter. You can think of it as the universe's invisible scaffolding, this cosmic glue whose gravity is the only thing holding galaxies together. And on the other side, you have dark energy, this bizarre cosmic accelerator that's actively pushing the fabric of space apart, making it expand faster and faster. For decades, we've treated these as two totally separate, mind-bending puzzles. But what if that's been the wrong way to look at it all along? There's a really compelling new proposal on the table that argues dark matter and dark energy aren't separate things at all. Instead, it suggests they both come from the very same source, the energy of empty space itself. The core idea is actually pretty elegant. It all comes down to something called vacuum energy. The theory goes that pockets of super-dense vacuum energy from the early universe got trapped by gravity inside massive galaxy clusters. This trapped energy, well, that's what we call dark matter. And at the same time, the huge pressure difference between this dense stuff on the inside and the lower density space on the outside creates an outward push. And that is what we observe as dark energy. One source, two effects. All right, so let's break this down. Let's start with the first piece of this puzzle. How in the world does this trapped energy idea explain dark matter? The concept is, surprisingly straightforward. Picture the very early universe. It was hot, it was dense, and its vacuum energy was off the charts. As the universe expanded and cooled, the energy level of the background vacuum just dropped. But, and this is the key, inside the most massive structures, like galaxy clusters, the incredible gravity acted like a cosmic container, trapping pockets of that original high-density vacuum energy. To get a feel for this, the paper uses a great analogy. Think of a galaxy cluster's gravitational pull as the steel walls of a compressed air tank. It's holding a super high-pressure, high-density vacuum on the inside, while all the space around it is at a much, much lower pressure. So why does this act just like dark matter? Well, remember Einstein's famous equation E equals mc squared? Energy and mass are two sides of the same coin. This trapped vacuum energy has mass, which means it exerts gravity, holding the cluster together. And because it's just the energy of space itself, it has no electric charge. It doesn't interact with light at all, making it totally, completely invisible. It checks all the boxes. And when you start comparing this idea to the hard evidence, the pieces just click into place. We observe that dark matter is invisible. Well, this trapped vacuum has no electric charge. Check. We know it basically only interacts through gravity. That's exactly what this model predicts. Check. And we see it concentrated in the deep gravitational wells of galactic halos, which is exactly where this model says it has to be. It's a really neat fit. But here's the real kicker. This model seems to naturally explain one of the very first clues that pointed to dark matter's existence, the fact that stars on the edges of galaxies are spinning way too fast. The gravity from the trapped vacuum in this model seems to scale in just the right way to produce these flat rotation curves without any special tweaks. It just works. Okay, so the model makes a really compelling case for being dark matter, but that's only half the story. For this to be a true, unified theory, it also has to explain that other cosmic monster, dark energy. And the explanation for dark energy is just as clever. It's not some separate, mysterious substance filling up all of space. No, in this model, it's just the large-scale effect of that pressure difference we talked about. Every single galaxy cluster with its trapped high-density vacuum is constantly pushing outwards against the lower density space that surrounds it. Now take that tiny outward push from one galaxy cluster and multiply it by the hundreds of billions of clusters scattered across the entire cosmos. Suddenly, that cumulative effect becomes this massive, universe-spanning force that's driving the accelerated expansion we see. It's not a substance, it's an emergent property of the universe's own structure. And the math seems to back this up. A quick back-of-the-envelope calculation gives a value for dark energy's pushiness, its equation of state, of about minus zero point -0.8. Now, that number is a huge deal because the standard theory assumes it's a constant value of exactly -1. This suggests dark energy's strength actually changes over time. So we have a compelling idea and we have a plausible calculation, but does any of this actually line up with what our best telescopes are seeing out there in the real universe? That's the billion-dollar question, right? So first, let's look at what the model predicts. It says dark energy shouldn't be constant at all. Its strength should have peaked billions of years ago, back when galaxy clusters were forming like crazy, and then it should have slowly started to weaken as that process slowed down. And this brings us to the absolutely cutting-edge data from the Dark Energy Spectroscopic Instrument, or DESI. And you just have to look at the trend. The data is hinting that dark energy isn't constant. It looks like it was stronger in the past, it peaked, and then it started to decline. Now, are the curves a perfect one-to-one match? No, not yet. But the overall behavior, the qualitative trend of peaking and then weakening, is remarkably similar. The model's big prediction of an evolving dark energy is broadly consistent with what DESI is just now starting to see. And that is an incredibly exciting sign. So, a single idea that could potentially solve both dark matter and dark energy, and which happens to align with brand new data, that is a massive development. And its implications could actually stretch even further to other big cosmic puzzles. Take the cosmic coincidence problem. Why do we happen to live at a time when the amounts of dark matter and dark energy are so similar? Well, in this model, it's not a coincidence at all. They both come from the exact same process. It might even help with the infamous Hubble tension, that big disagreement over how fast the universe is expanding, because an evolving dark energy would naturally change that expansion rate over time. But, and this is really important, we have to remember this is a compelling hypothesis. It's not a finished, proven theory. There is so much more work to do, from building out the full, rigorous mathematics to stress testing it against every piece of cosmological data we have. This is science in action. It's messy, it's exciting, and it's a whole new path to explore. Still, it leaves us with this really profound thought. For the better part of a century, we've been searching for answers in the dark, looking for some exotic new particle to solve our problems. But maybe, just maybe, the answer was never in a particle at all. Maybe it was here the whole time, hiding in the dynamic, powerful, and far from empty emptiness of space itself.